So this is I mean straightforward in case of this oscillator, and we know for dual edge modulation, let me just okay. So for dual edge modulator we can do with the oscillator because it is not possible with the these current sources. But what do we do here actually? I mean this is possible with the current source in this case, and here we are limiting only one side voltage, not two side voltages. So whether you use a oscillator or you use this simple ramp generator, how do we make sure that my common mode remains at VDD by 2? Because we are resetting at 0, whether you take this oscillator. So in this oscillator, this MOSFET will reset to 0 ground, and again if you talk about this leading edge, set to VDD. So you are always starting from 0 or VDD in this case. So you are shifted towards VDD or towards ground, your ramp. Your ramp common mode is not at the mid VDD. So this may have a problem. If we take the case of this, you cannot operate it lower duty cycle. Let us say the moment it goes below below 110% or so, and if my VM is 1 volt, then that voltage will control voltage will drop to 100 millivolt. So at 100 millivolt or lower voltage, I cannot ensure that this NMOS will remain in saturation and my error amplifier gain will drop. So how do we fix that? What can we do? You have to simply modify this circuit to shift the common mode. So what? Yeah, you just replace the ground with the another voltage, so that it will always reset to that. So let us say replace the ground with 0.4 volt, and you keep everything else same. So it will now, instead of 1 volt, it will charge to 1.4 volt because you are starting from 0.4 volt offset. So So where do we want to keep this? VDD minus VM by 2. So what do you require in that case? How do we shift this? How do you generate this ground actually? So one way could be like, so if you have Vref equal to and this buffer will be connected to this guy output, but it will require a huge cap because all of a sudden you will be resetting it, which means capacitor has to discharge. So this capacitor should be okay. Because if this capacitor is large, only then it can bring the voltage of the other cap to its level. Otherwise, if it is a small, then it may not discharge. I mean, it may remain much higher. Okay, so it should be a stronger cap. It's just a charge balancing is happening, so it has to draw all the charge from the smaller cap, which means this capacitor should be large enough. What could be other way, simpler way? If I don't want to use this, but I want to keep roughly at, I mean this needs not to be very accurate, VDD minus VM by 2. If you are off by plus minus 100 millivolt, that is also fine. Can we use some other way where I may not be very accurate, but still I can achieve the same kind of behavior. What if I use a PMOS to reset this? Instead of NMOS. This is ground. So, when PMOS input is 0, this will turn on. What is the maximum voltage it can discharge to? VT, huh? And this will be how much? Vm plus Sp. And this is roughly 500 millivolt. So, still okay. You can use a little bit larger device, so you can bring this 500 millivolt close to 400 millivolt if you want. And if you are operating at a much higher voltage, let us say 5 volt or so, then you can stack multiple PMOSs and use 2 VT, 3 VT, whatever you want. Okay. Similarly, for the leading edge, we are setting this, basically we are charging this to VDD through PMOS. If we do NMOS, then it will limit to VDD minus VTN, that is it. Okay. So, these are the like small things you need to take care when you are designing your DC-DC converter. So, you have to look at I mean, let us say your operating voltage is output operating voltage is always more than 50% of VDD, which means like you are always above 50% duty cycle. Then you can basically you do not need to care about the lower level of the voltage, because you know your control voltage will never go below Vm by 2. So, in that case you can use this ground basically to reset your RAM. So, in that case this may work, this or this, both will work. Okay. So, if you are using this kind of RAM generator where you are resetting your RAM to VDD, or if it is a leading edge, or for trailing edge you are resetting your RAM to 0 volt, then which one to use you can decide based on where the duty cycle is lying, whether it is you are always operating below 50% or above 50%. If below 50%, then you go for leading edge, okay, because then your control voltage will always remain above Vm by 2, in this case above 0.9 volt, or VD by 2, in the other case not Vm by 2, but VDD by 2. And in the other case if you are operating at below 50% duty cycle, then you can have your I think that was correct, Vm by 2, because we are going from 0 to Vm. So, 50% is Vm by 2, we are not changing the common mode here. So, as long as we remain above 500 millivolt, and you are always you are not going basically closer to so you have to see where are you limiting the duty cycle actually, whether you are going hitting the voltage where one of the devices will go into the saturation or not. Okay. So, let us say my range is maybe 20 to 60%. Okay. So in that case, the other, I mean, other case may work. Okay. So, but if you are, let's say you are going on the higher side from 50 to, you are operating from 50 to close to 100%. In that case, 50% is not a problem for trailing edge, because so your ramp is always 0 to 1 volt. So 100% will be your 1 volt control voltage, which is still much lower than your VDD. So still you will have a 0.8 volt headroom. Okay. And I know I will never hit the lower voltage, because my operating duty cycle is not going below 50% or so. So your amplifier will be, or the output stage of your amplifier will be in saturation, always saturation. So that is a one way, but if you are operating at the entire range of duty cycle, then you have to shift the common mode, you do not have any other options. So you have to decide based on what your specifications are. So if you remember, this is what we had for type 3 compensator, and we had another capacitor, this, we call it CD, CI, RP, and this is your V control. So this is the op amp or your error amplifier. And your compensation network is built around that. So one thing you need to consider actually, bandwidth of op amp should be high enough not to interfere with loop gain transfer function. Okay. So what we want, I mean, we don't want additional pole from your op amp, because here we are introducing an integrator with 2 zeros, and then on top of that we put 2 more poles, if you remember, high frequency poles, due to noise reasons. So one more pole means getting, even if it's not inside UGB, but even if it's, let's say, even within, let's say, 4 to 5 terms of UGB, still you will get a significant drop in phase margin, I mean maybe 5 to 10 degrees, which is significant. So that's why we don't want the pole due to op amp interfere with your loop gain transfer function. So that's the one thing. Most of the time, if you keep op amp omega UGB 10 times of your DC to DC. Okay. So if you remember the example we took for 1 megahertz, 100 kilohertz was the UGB. So you want to keep it maybe 1 megahertz or so. So, and you can always model this. If you want first order approximation, you can just replace this op amp transfer function with the first order. So if this is AS, then AS equal to A naught over 1 plus S over omega p. Okay, so omega p will be the 3 dB frequency. So UGB of op amp will be A times of omega p. So that UGB should not interfere. I mean, that's the UGB which you want to keep outside your UGB so that you get enough bandwidth. Because one thing you have to remember, this op amp is not in the open loop. We have a closed loop network around that. So that's why we are not looking at a 3 dB, but if you want to keep 3 dB at 100 kilohertz, then you can imagine what kind of UGB required, order of gigahertz also. So which is almost impractical. So whenever you connect any op amp in a feedback, then you always look for UGB. So because at high frequency this will be shorted, so you can treat it as a, I mean, even if you have this and this will also be shorted, so it will more act like a unity gain amplifier. So in that case, until UGB you see a flat response. After that, so 3 dB is shifted to UGB in that case, in the closed loop. So let me just, so one thing I mentioned yesterday that I was talking about the resonance, so I'll just show you what happens. If you want to really see why this is occurring, you can just replace this op amp transfer function with this and then derive the compensator transfer function again, and you see how does it affect actually. It will basically, you will see some additional resonance frequency in the in your loop, actually loop gain. So one resonance is coming from LG, other resonance will come L and C, and another one will come from this one due to the limited bandwidth of your op amp. So what I did, this was my original circuit, and I replaced this op amp with the first order model. So you have a voltage controlled current source, then I have RC at the output. So GMR will be your gain. So I'm keeping 1 milli and 1 mega, so it's a 60 dB gain, and the same 1K here. So I try to keep the same, and then you have a buffer to make sure it's this is not 1 mega ohm is not loaded with that at high frequency. So it's 160 femto. So 160 femto. So this will give you 1 mega. Once, I mean, if you just do 1 over 2 pi RC, and this is at 100K. So what I did actually, this was 1.6 pico. I made it femto, which means this capacitor is out of picture, and this resistor was 5.5K. If you look here, the value, I made it 5.5 milliohm. So which means I'm trying to get rid of these two high frequency poles and see what happens at the. You can see here the resonance, okay, and this is not far away from your 0 dB, it's minus 7 dB. So still you might see some ringing in the output, and if you this is occurring at high frequency, if I reduce the UGB of this, then this will shift at lower frequency, and which means this peak may even touch your 0 dB or it may cross, so it may make your whole system unstable. So if let's say I increase, so right now it's 1 megahertz, I make it 16 femto, so this will become 10 times. So let me just have this, and on top of this I'll plot the other one. So you can see it has shifted much away from, I mean, it's coming around like beyond 10 megahertz also, okay, and since gain is also dropped, so you will see that resonance peak will also reduce. So that's why if you don't have those two high frequency poles, you may require a very high bandwidth here, which means that will come at the cost of current consumption. Okay, so let me just go back, and so I'll keep this and I will add those poles. So that resonance went away. So that's another benefit of having those two high frequency poles. It will try to suppress any resonance which might occur due to the limited bandwidth of the op amp or the poles which are in the op amp. And if you replace it with the second order, this resonance may look even worse actually in that case. We are just having a first order approximation here. So that's why it's, you might think that, okay, let's try to move this pole maybe at much higher frequency, or just get rid of this to get a better phase margin, because they will, they will cause some drop in the phase margin, maybe 5 degree to 10 degree something. So if you try to get rid of this just to increase the phase margin, so then you have to be a bit careful that you may have that resonance and it may basically cause some kind of instability in your loop. So it's okay to have 5 to 10 degree. If you are looking for 60 degrees, if you are, instead of that you are getting 55, you may still be okay, but that resonance is not good actually. Okay, or otherwise until unless you make your op amp bandwidth very high, which means you may have to burn lot of power in your op amp. So which means second high frequency poles when I say high frequency poles, I'll just mention outside omega VGB. Okay. Okay. Yeah, but this problem will not occur if you are using GMC. Okay, GMC is everything is open loop, so you won't see any resonance or anything there. So your design may become a simpler with the GMC, because instability problem may not happen there. But when are using op amp, because everything is connected in the feedback, then things become a bit complicated. Yeah. So if you can design your GM in such a way that your offset is not that high, then you may prefer to go with that if you are having any issues with the op amp. So the gain requirement, if it's 60 dB, then you may go with a simple two stage. Okay, and if your gain requirement is let's say a bit lower, then you can go with a single stage also in that case. And another way, with a single stage, if you want to increase the gain, you can go with telescopic, where you cascade in the single stage and get the higher gain. So by increasing your R out. So you are free to use any op amp topologies, folded cascade or your simple two stage or telescopic, as long as you meet the performance. So that's your choice actually.